Well, hello everyone. I'm here with little Odie today because we've got some things to talk to you guys about. Namely, some of the traits that he and I share. Good boy. So you'll notice that we're both mammals. We both have our 4 limbs. He likes to shake paws a lot. He's got some digits. He's got some hair. I've got some hair. And all these traits give us an idea that we are both related to one another as mammals. But there's a lot of transitions in between us, right? These opposable thumbs that I've got, the differences in our face, the differences in our ears. Even though we are both mammals, we are unique because a lot of our traits have changed along the tree of life. We can oftentimes use these traits and changes in studying a lot of our fossils. Fossils give us a glimpse back in time. And so that's going to be the focus for this next set of labs. We're going to be looking at evolutionary biology and seeing how life has changed throughout its history on planet Earth. But before we get to the real stuff, we want to get to some toy examples. So that way y'all understand how we build phylogenetic trees and can do so on your own. So to explore this topic, we're going to begin with communicules. Now you'll see these in your lab. They'll be slightly differently than the ones I've drawn here up on the board because I'm not quite as good of an artist as Kamoon, who drew these things in the first place. But the point will still be illustrated. In our first exercise, you are given an outgroup, which is our most basal form on the tree. So something that we're going to be considering our ancient living relic. And then 4 modern day communicules. And it is your job in this lab to figure out which traits you're going to use to connect these in a phylogenetic tree. Now, drawing on your information from lectures, you'll remember that phylogenetic trees are built by connecting 2 endpoints in such a way so that the 2 that are connected first are more closely related to one another than the connection that comes behind. These 2 are considered our sister taxa, are more closely related to one another than either of them is to C. Now, how do we build these basic character trees, these basic phylogenetic trees? Well, we're going to do so with character state matrices. And you're going to be building a lot of these. I want you to get in the habit of doing so. The basic premise behind a character matrix is that you're going to have different characters. Maybe you're looking at the shell of the organism, the arms of the organism, the feet of the organism, the eyes of the organism, adding more and more traits. And then you will list the different states. The ancestral state, or the state that you're likely to find in the outgroup, will always be coded with a 0. So every single one of these will have an ancestral character state. That state is assumed to be the one that occurs at the back of the tree. So going back to draw our CAB analysis, whatever the ancestral trait is the one that's at the root. The trait at the root is inherited by all things down the tree. And if you want to change the ancestral trait, it'll cost you. And we're going to represent those costs by drawing tick marks on the tree. So for example, if it was 0 at the root of the tree, C will inherit 0. It can change to 1 between C and AB, and then A and B will both inherit the 1 character state if you put the tick mark here. In this way, we are trying to utilize the least number of tick marks in order to explain all the character state changes in our tree. This principle is called maximum parsimony. Or as one of my biology professors said early in my career, keep it simple, stupid. You don't want to overly complicate things. You want to use the least number of transitions possible, and so we're going to be doing so in our character state matrices. So for your first task, go back to our 4 organisms, decide what are the ancestral states of all of these three traits, assign them alternative states, and then give each of our species, A, B, C, and D, one of those states. From there, once you're done with the matrix, I'll fill in my own, and we'll see how we build a tree from there. See y'all in a few minutes. All right, welcome back, everyone. So hopefully you've had some time to stare at these communicules and think about how to make our character state matrix. So Beck and I have discussed things, and in looking at our outgroup, we've decided on all of our outgroup states. So our shell, our character state 0, is to be a shell that has a lump. Something similar to this individual right there, because you've got much the same shape. Our transition, therefore, our value of 1, will be assigned to a smooth, along almost hot dog bun shaped shell. Now for our arms, and keep in mind, you want to be focusing on one character at a time. When you're talking about arms, you want to pay attention to the arms themselves, not the fingers. So we are very distinctly only talking about the arms themselves. In our outgroup, the state is easy again. No arms. Does not have them just yet. And we can't tell. There's no evolutionary hint, at least as I can tell, whether bent arms or wavy arms came first. So, with that amount of information, we'll give it a character state change of 1. Then it can be either wavy arms or bent arms. And last but not least, for this first draft of the tree, we'll look at our feet. The outgroup has no feet. And then we've got a couple of different transitions. Now, I'm going to interpret the fact that the simplest set of feet, a nub, will be our character state 1. From a nub, then you can involve these fins. These will get a character state of 2 because it will be one additional change from there to get that pronged fin. Once you have the fin, then maybe 2 different feet can come along. And so by setting up my character state matrix with these 3 different states, what I am saying here is that there is an evolutionary progression. You don't go from no feet to feet. You go from no feet with a cost of 1 to a nub, with a cost of another 1 to a fin, and then from fins themselves, you can then evolve 2 separate feet. So there is information to be gathered in the way in which you set up these character states. So let's go ahead and assign numbers to all of our different groups. Becca, what do you see about the shell for A? Do you think it's lumpy or smooth?
That one's smooth.
All right, so we'll give it a 1. How about the shell for B?
Lumpy.
Yep, that looks like our ancestral trait. How about C?
Smooth.
Again, we've got our smooth, and D, another smooth. Now how about our arms? Well, they all have arms, and they're all either wavy or bent. So we're going to give them all character states of 1. And now for our feet, A, here with our fin, we're going to say that it has a state of 2. B, with our nub, character state of 1. Our individual C, with proper feet, gets a 3. And our last but not least D, with the fin, will get another 2. So in order to establish these relationships and see which one of these is most closely related to our outgroup based on these 3 traits, we need to sum up these values. So individual A has a total value of 4. Individual B has a total value of 2. Individual C has a total value of 5. And individual D has a total value of 4. with these summed values, we could start drawing our relationships. The lowest value is going to be the one that's the closest to our outgroup. So if the outgroup is the root of the tree, you can represent it as the root or the first group that comes off. If it's still alive, it will be a group that comes off here. And then we'll say that the thing closest to it was B. And just like I talk about in the lectures, for now, assume nothing by the length of the lines. Length here, since I'm a human being drawing these and not a computer, length is not informative. You're just using it to establish relationships. Look for which lines connect, not how long those lines are. Now next up, we found ourselves in a conundrum. A and D both have a value of 4. And on top of that, they've got the exact same numbers in each of these traits. Now what we would do as scientists is see if we can add more traits into the tree. See if we can separate them. Because, Becca, I think you and I would both agree that A and D are both vastly different from B. And that they're different from each other. We should be able to separate them, right?
We should.
But for now, we're just going to group them together on one single node. Since we can't tell who's more closely related to whom, we're going to have A and D on their own line, connecting with one another before they connect with anything else. And that leaves us with our last but not least, C, individual, with the greatest distance 5. Now, come a little closer so we can put our tick marks on the trees here. Because we're going to want to show everyone how we're going to establish these relationships and how they transition. Well, in going from our outgroup to our individual B, what are some of the changes that we see? We're going to plot those as tick marks along the tree here. Now we see a change in arms to character state 1 and a change in feet to character state 1. So for shorthand here, I will put arms 1 and feet 1. That costs me 2 points to the ultimate length of my tree. There are 2 tick marks on the tree. With those changes, we can arrive at the common ancestor of B. Now in going from B to A, D, and C, we need to figure out which of these changes are inherited by A, D, and C all together if we're going to put them on this span of the tree. Those that are specific to A and D only will go here, and those that are specific to C will go here. So we have 3 different regions where these tick marks are going to go. Putting them at the base will cause all descendants to inherit it. Putting them at the base of A and D will cause these 2 descendants to inherit it. And putting it at C will cause only C to inherit it. Does that make sense? So the first state change that we're going to see is that they all change their shell, right? A, C, and D all have a smooth shell. So one of the tick marks going here will be shell to a character state of 1. Now what other transitions are we getting? Well, we're pretty much already done with arms, so you can ignore that. And we're done with shell. You can ignore that one for the rest of the tree. So the rest of the tick marks are going to be about our feet. Well, we know that they all change from a 1 to a 2 or a 3. So we can put another change adjacent to this shell change of feet changing to the 2 character state. It goes from a 0 to a 1 in B, and then from a 1 to a 2 in A, D, and C. But we know that C has another change of feet 3. Now, because we don't have any of our other hypotheses about these individuals, like maybe looking at the color patterns on the shells or something like that, we don't have a change that makes A and D separate or is shared by both of them. We just have one that is separating C from A and D, being our feet transition to 3. And so this is our tree. If we're going to redraw it with a little bit of simpler notation here to be not as confusing. The out group comes first. B will be after that. A and D are sister taxa. We get the transitions here of shells to 1 and feet to 2s. And then C is going to get a tick mark of feet to 3. And we ultimately have a cost of 5 in building this tree. 1, 2, 3, 4, 5. Hopefully this made sense to you, and hopefully you started to notice that I could incorporate more traits to build a more defined tree, establish better connections and more confidence in these relationships the more character states I include. So your task now is to take a moment, add some traits that you see in either the individuals on the board or individuals that you have in your lab, and extend that tree. Once you're done with that, I'll see y'all for the next component of our exercise. All right, so hopefully you've had a chance to add some more traits to your tree, but I want to spend a moment talking about some of the discussion questions that you're getting after you change the topology or the connections. Topology, just like topography, the connections, the way in which the landscape of the tree changes as you build more things onto it. The first question on there after topology is looking at the closest evolutionary distance and the furthest. Well, we actually don't have a distance between A and D. They are functionally the same thing because our traits do not separate them. So, evolutionary distance is 0. For our furthest evolutionary distance, you can look between C and B. You have to have 1 character state change, 2 and 3 character state changes before you can get B and C to unite. They're pretty much as far apart as we can get. Now the 2 really hard questions, or more complicated ones, are talking about the information that you gather from these different traits. The first asks you which traits were non-informative to your clustering. And you will get some of these when you're building your trees. Some traits just don't actually help you cluster anything. To identify these, you're going to take a look at a trait that's shared with all of your descendants, but not your outgroup. So yeah, they're different from my outgroup, but this doesn't help tell me whether A was closer to B or C or D, because they're all the same. So arms is considered our non-informative trait in our original character state matrix. Now, the opposite of these non-informative traits are those that seem to be very informative in building your relationships. Here in our example, while shell did help us establish that B was the closest to the outgroup, it was really feet that helped us separate A and D from C. So feet gave us the most topographical resolution in our phylogenetic tree for this example. Maybe it's different in your tree. I hope it is, because there are a lot of different traits that you could use to help cluster things differently. But we do see the difference in how much information we can gather from each of these traits. And as we travel down the evolutionary tree of life, you'll notice that some traits that are very informative early on, like shape of scales in our fish, are completely useless when it comes to me, or little Odie, who happens to be sniffing things back over here, because he and I don't have scales. We've evolved to have hair or fur. Now, interestingly, the proteins that build some of that hair or fur on us are actually the same as the things that build scales on reptiles. So it does depend as to how you're looking at these things, at a molecular level or at a structural level further above. Now with all that stated, and hopefully with some more traits on your tree, I'll bring Becca over here and we'll have a discussion on some outgroup selection before you build the big tree of this lab. All right, so now, hopefully you've read this part of the lab where we're talking about outgroup selection. Because outgroup selection is going to be very, very important in so many different examples in this class. Outgroup selection is a classic Goldilocks problem. You don't want something that's too far apart, nor something that's so close that it might group within your species. This means that sometimes you'll have to change which outgroups you select. Generally speaking, you'll want something that represents the old ancestral state in your tree. So for example, if you're trying to look at all mammals, meaning you're looking at platypi and marsupials and Odie and myself, a good outgroup for those would be something like reptiles. They are sister to all mammals, but are different enough that they're not going to group within the mammals. But they're not so different that you can't recognize the same traits. Reptiles, for example, do have those 4 limbs. If you picked something too far apart, like maybe an octopus, it would be very difficult to infer what some of those ancestral traits are. Hopefully that makes sense to you as to what our Goldilocks problems in terms of outgroup selection can be. So, with that, we'll go ahead and take a look at the major data set that you're going to be building your giant phylogenetic tree from. And now with these 12 different communicules, Becca and I have each selected separate individuals that we think are the outgroups. Now, generally speaking, we're going to be looking for some of our more simple organisms, things that do not have as much complicated features. So, that might eliminate some of these more complex individuals and leaves us with 2 strong contenders. Now, Becca, which of those 2 did you pick and why?
I'm picking number 8 because it has a more simplistic nose, face, head, whatever you would like to refer to that as.
Very justifiable. Without some fossils and without some molecular data, we'll never really know. So, sounds good to me. Now, I'm going with number 7 because I see that number 8 has these little appendages for arms. And I think that arms are a more complicated feature than having no arms, so I would say number 7. And if I'm saying number 7 is the outgroup for this tree, then I'm assuming that this state of face is ancestral. In some cases, you can get simplification of features. And we do see that a lot. Features that were complicated can simplify, and features that were simplified can become more complicated. You just have to make sure to code up your character state matrices appropriately. So now, this will be the bulk of the exercise for the lab. Go through and with at least 5 traits, using these images of communicules, build a matrix and a phylogenetic tree connecting all 12 of our communicules. Keep in mind that there are over 50 of these designed, if you want to go online and look, and Come In actually has fossils, in case you want to look up some of the transitional fossils. So have some fun with this. I think it's a great exercise. And we'll see you on the other end, where Becca and I will do some rapid fire group placement based on some overarching traits. Have fun with this one. All right, so hopefully y'all had fun making that big old tree from our 12 different communicule species. For our last little exercise, this is something fun to do with another individual. Here I've printed out 29 of our communicules, and I want y'all to identify rapid fire groups for them. So the goal here, maybe use a whole bunch of different colored pencils and establish groups. You're gonna want to select groups where there's more than one individual, and you're going to want non-overlapping groups. So to get us started, the first thing that pops out to me when I'm staring at these is I see the dragon-like communicules. Whoop! Of course the colored pencil breaks on the first circle. So I select these 4 that have very long shells, dragon-like communicules, and they're out from the pool. Becca, you're up next. What's your grouping?
I want all of the ones that have camouflage in their shells.
Ooh, excellent choice. That's a large group. Now that really would help us in designing the phylogenetic tree, but you can see that there are differences in the camouflage, so it's possible that these are a group that exist on many different branches. Now, I'm going to be selecting, let's go with those that have wavy arms left over. So, the communicules that look like they're riding a roller coaster. We see that they, again, share traits with a lot of other groups, but at the very least, we can group them together by those wavy arms. We've done a pretty good job selecting groups since there doesn't seem to be that many outside of our selection criteria. Becca, what's up next?
I'm going to say the ones with little arm nubs that we were talking about earlier.
Ooh, very observant of you. Okay, and that leaves us one group, one final, most simple group. I'm going to go ahead and say that these group along the basis of having the fewest derived traits. Maybe a little bit of a nub at their tail, giving us an idea of what might have been the outgroup to all these 29 different communicules. So identify several different traits. Becca and I grouped all of these with 4 different traits, as you can see with the 4 different colors. You can do so in 3, in however many, but this kind of thinking about traits as a grouping mechanism will really help you in building your phylogenetic tree of life, because there is so much diversity of animals on planet Earth. So with that, please make sure that you all define the vocabulary in this lab, and we will see y'all next week when we dive into actual fossils.